no further ado, I'll hand over to Affie, who's going to go through the spec of it.
So there are two topics I'm going to talk about today. So the first one will cover an overview of OpenCL. I'll talk about some of the design goals that went into the OpenCL specification, followed by discuss really the key architecture. What are the things that drive OpenCL execution model? Then maybe dive a little bit into how to use it and what's the language for writing the thing we call kernel, this piece of code that executes in parallels. And then we'll go into 1.1. We'll talk about some of the new features that are in 1.1, give it some reasoning behind why these features were added. So let's talk. Well, so on the CPU front, we see multiple cores, not multiple megahertz driving performance. This is everybody's aware. An application really needs to be able to take advantage of these cores to get speed ups in the application. The GPU we know now is a general purpose computational processor. We also have other processors we call accelerators, such as the cell processor or DSPs. So a modern platform contains or may contain one or more of these devices. And so one of the key design goals is that we want to be able to have developers use all the computational resources in the system. So CPUs, GPUs, accelerators are peers. And so when we talk about the computational model, we have two extremes. One we call a data parallel computational model. And put simply, what we are saying is we want to execute this piece of code, and it gets executed for every element in the data set that I want to operate on. That's a very simple view of data parallel computation. OpenCL certainly implements that, but it also gives you much more flexibility in terms of how you could have the mapping doesn't have to be a one-to-one mapping. And I'll talk about that a little bit later. And on the other extreme, we have tasks. Here's what include tasks. So a lot of things we find that applications do is a combination of queuing of work that contains just tasks, the shared data file kernels, and you want to basically have some form of control that controls how these things get operated. So that is one of the key driving design decisions behind what it needs to be able to support and support well. Then we talk about, well, how do I write this code that's going to execute parallel? So we wanted something that was efficient and allow developers to get close to the middle performance as much as possible. And familiarity with C basically was one of the main reasons why we chose a subset of C99. And clearly we wanted to abstract the specifics of underlying hardware so that we can actually provide wherever possible a portable performant interface for some of these features. It is a compute API, so it's really essential that we want to be able to specify the accuracy of floating point computations. So I won't actually go into the details of how we define the accuracy of floating point computations, but put it simply, it is a subset of IEEE 74/2008, and we actually enforce that very heavily. You can talk to the vendors about conformance tests, through conformance testing, and then we talk about desktop and handheld profiles. So handheld devices have additional constraints because of power and other reasons. We wanted to make sure OpenCL is not just designed for desktop systems, but actually for all of these, a number of environments, which include desktop and handheld devices. And so the way the specifications have been designed with the handheld profile actually is a pure subset of the desktop profile. Okay. So let's talk about some of the key architectural concepts. So we'll talk about what we call the platform model and an execution model and a memory model. And so you will see the specification broken into a platform API, a runtime API, and then the language. And so there is somewhat of a mapping here between these architectural concepts and how actually it gets implemented as APIs. So the platform model, put simply, is it's a host connected to one or more devices. In fact, the host could actually be an OpenCL device. And a compute device is just a collection of compute units, and a compute unit is just a collection of processing elements. And these elements execute code either in a SIMD or an SPMD fashion. So that's very simple. So you will actually find in the platform model there are APIs that allow you to query what platforms there are, what devices are supported by the platform, and get all kinds of information about capabilities of the device. So let's talk about the execution model. So as an application, I want to be able to send work to be executed on a device. So in order to send this work, I need to queue this code somewhere. And the concept, how you do that in OpenCL, you have a command queue. So you find out the devices and then you create a command queue on the device. Okay? And the code that you want to execute in parallel, we call that a kernel. Okay? This is analogous to a function. So when we say execute this kernel, analogous to executing a function call. Collection of these kernels and other functions that they call, we call it a program, and that's analogous to a dynamic library. The thing, the element of execution that executes this piece of code, kernel, and we call that, that's the basic element of execution we call that element. And all of these things are wrapped around this concept of what we call a context. So the context encapsulates the devices and all the objects that we want to use to allocate data, objects we use to send work, command queue. And so think of your context basically as a process. So sharing of data happens within the context, not across context. Yeah. And queues, we have two kinds of queues. So all work always gets queued in order, but they may not necessarily be executed in order depending on the property of the queue. So the queue can be an in-order queue or an out-of-order queue. And I'll talk about that in a few slides. So what is the big idea behind this? Well, let's illustrate that with a very simple example. Let's say we have, I just want to take the product of two floating point arrays, and these arrays have an element. So typically, a traditional way of writing this code would be well, this is a classic example of the data parallel operation. So all I need to do is describe the inner loop. And I need to be able to find out for a particular instance that is executing this inner loop, which data element am I referring to? And that's this concept of get global ID. We'll talk about that in a little bit. So the big idea really is very simple. You define the computation domain for which you want to work. So in this case, it's a one-dimensional computation domain of size n, where n is the number of elements. And we just go execute the kernel at each point in the computation. So that's the idea. So that means I need to now define the global size. This is what we call the total amount of work that a kernel is going to work on. We call it the global work size. And that can be a one-dimensional, two-dimensional, or three-dimensional. In the previous example, we were just operating on arrays, so it was a one-dimensional. If I'm operating on an image in here, each pixel could be executed in parallel. So a better way to describe the total problem size here is a two-dimensional, not a one-dimensional. So in this case, it's a 1K by 1K image, so my global work size is 1K by 1K. Now, there are many cases where, so all of these work items are executing in parallel. There are many cases where I actually want to group work items together because I want to share data between them. So let's take a simple classic example of, I want to generate the sum of the elements of an array. One way you could implement this in parallel is you can break them into generating sums of subarrays, and then you can keep the sum, generate the sums of the subarrays, and finally, after log n steps, you will get the final sum. Well, to generate the sum of the subarrays, I actually need the work items that are generating partial results to be able to share that. So there are many cases where I actually want to group work items, so I share data between them. And we call that a local work group, and we call that the local size. Okay? So the idea is you choose the best dimension or the size of your computation problem based on what you're working on. So in this case, example, I chose a work group size, global size of 1K by 1K, and a work group size of 128 by 128. Now the key thing here is that work items in a work group can share data, and they can perform synchronization between each of the work items in the work group. But there is no such thing across work groups. And the reason for that is simple. Remember, the work groups execute on the computer, but the number of work groups that we have launched here, there are many, would be executing concurrently on the same or other compute devices. So it's not possible for you to know when a work group gets executed. So it's not possible to synchronize across work groups. So let's talk about the memory model. It's a hierarchical memory model. And so we have the host where the application data originates. And then we have global memory. This is the memory on the device itself, the GPU, DRAM. And then this is visible to all in the API. So why do we need to worry about this? So we talked about queues being in-order queues or out-of-order queues. Well, what is an in-order queue? So let's say I have a queue and I want to set commands A, B. I have queued commands A, B, and C in this queue. An in-order queue B begins execution after A has finished, C begins execution after B has finished. So, makes sense. In an out-of-order queue, there's no such guarantee. C can actually start executing before A and B. And that's great because that reduces the level of asynchronicity in the system, which is helpful for performance. And if A, B, C are operating on data that's completely distinct, that do not share, there's no sharing going on, absolutely, I want to be able to do that. But if they are sharing, so let's take it, B wants to, kernel B wants to use data produced by A. You clearly don't want B running before A. So how do I, so I need a mechanism to be able to say when a command that I have in queue can execute. This is true not just for an out-of-order queue, but it's true even when I have multiple queues, even if they're in-order queues, for the same device or different devices. So the way we handle synchronization is through events. An event identifies a command, and every command in OpenCL, every API in OpenCL that engages a command takes these three arguments. The events to wait for before this command can execute, and the event that identifies this command. So let's look at how we can use this. So let's take a simple example. I have two queues, one on the GPU and one on the CPU. They're in order queues, and I am going to enqueue kernel 1 to the GPU, and I'm going to enqueue kernel 2 to the CPU. Well, if there were no synchronization of primitives used, then it's possible that kernel 2 can start executing before kernel 1, which is not what I want. So I want to take the event as returned by kernel 1 and wait on it before kernel 2 starts. And so that's what you are able to specify. So there's much more fine-grained control of how commands get executed. So let's talk about the language. So OpenCL C is derived from ISO C99. It's a subset. So it does not include features such as function pointers, variable length arrays, recursions, big fields, and things like that. But there are a number of extensions, features added specifically for parallelism. We talked about n-dimensional computation domain. So in my kernel, I need to know a lot of information, like what particular data element am I operating on? What kind of operating on? How big is this domain I'm operating on? Things like that. Support for vector types, and this is really crucial because you no longer have to worry about the underlying ISA. The compiler produces code for depending on what device it's compiling for. So if it's a CPU, an Intel CPU with SSE, we will generate the compiler will generate the right SSE instruction. And then we talked about a memory hierarchy. So we need to declare what data, memory regions the data belong to, and so there are address space qualifiers that are added to the language. And then synchronization primitives. So there are synchronization primitives from the API, there are synchronization primitives in the language. Okay? And then there's a rich set of built-in functions. And I'm warning you, there's a trivia question on this, so be prepared. Says functions to all the math functions that are defined by C99 and math.h are supported. There are functions for reading, writing images. There are a bunch of integer functions. There are functions for doing permute. Very useful if you're operating on vectors. The thing you want to make sure is you don't do a lot of conditional code, so that's bad. So you want to do permute. So what is this thing called a kernel? Well, if you have a function in your code, all you have to declare a qualifier, say this is kernel, and that makes it marshal a kernel function. But along with that come a lot of rules about what kind of arguments it must take. And I won't go into a lot of details on that. And the return type must always be void, right? We talked about, okay, so this is a data file kernel. It's describing the inner loop. I need to know what item am I operating on. So this is the get global ID function that says, oh, this is my global ID. Okay, so in this case it's 7. So I know I can take element 7 from input and then do whatever operation I need to do, and I write to output index 7. Well, what else?